All right. So your last chapter, we talked about Euler circuits and paths. And Euler was every edge needs to be used exactly once. Okay? Every edge. This chapter, we're going to look at Hamilton circuits and paths. So same type of an idea, but your difference is Hamilton is looking at touching every place once and only once. So you're going to every dot once and only once. So formal definition for Euler was must touch every vertex, and we can only, so must touch every vertex, can only cross edges once. Again, Hamilton is using every vertex once and only once. So, by definition over here, not every edge has to be used. Not every edge has to be used for Hamilton. So, you're cool with Hamilton, and I always think about it. This goes a lot better with girls that like to go on shopping sprees, and you know you've got to go to Target, you've got to hit Route 21 and all these places. Okay, you're not going to go to Target and then go back to Target. Okay. Listen, no, we don't forget things at Target. You make a list, you go there, and you leave. You don't go back. Okay. You don't like Target?
It looks like a
my
Maybe you should have said
sister-in-law.
Old Navy.
I told my sister-in-law, I was like, I hate Target, and she goes, we can't be friends anymore. I need you to leave. She is obsessed. It's, I don't know.
It's not even that great.
I don't care all that much for Target either. I shop at Walmart
I don't care for
and I shop at Goodwill.
Goodwill, Ross.
Listen, I can go to Goodwill and I can find stuff with tags still on it for like $4, and that sucker was like 80. I was like, get out of here. I don't care.
You gotta go to Goodwill in like Charlotte. That's where you go.
Go to where in Charlotte?
Go to the Goodwills around Charlotte. That's where you get a bunch of good stuff.
I like the one in Knoxville.
Yeah.
I like the one in Knoxville.
Like my brother found a pair of Kobe 12s. $2.
All right. So we're going to review Euler paths and circuits with all of these graphs, and then you're going to be able to sit here and look and see if you can tell me if we can find a Hamilton path or circuit. So we're going to kind of do the whole thing that we did at the beginning of last chapter, where you had to try to come up with the rules.
So are we gonna like label?
So, graph 1. Remember, if I have a Euler path or circuit, how do I find that? Even and odd, we've got to find all of your degrees of your vertices. So, take a look at graph 1. A has a degree of 2. Okay, let's just go around to the right and then we'll go to the middle. B has 4, 4, 2, 4, 4, 4. So, it's all even, which means what? This is a circuit. Graph number 2. We're going to do all of Euler's first, and then we're going to go back and look at Hamilton. Okay. So we're at 2, 2, 2, 3, and 1. So this is a path. Fantastic. Okay. Graph number 3. 3,
4 in the middle.
3, 4 in the middle, 3, and 3. So Dakota, what? Neither. Okay. That's a neither. You've got more than 2 odds. Graph number 4.
Circuit.
That is a circuit. 2, 2, 2, 2, and 4. This is a circuit. Okay. Graph number 5. This one is a path. Good. and graph 6?
Neither.
This one's going to be neither. You've got A is odd, B is odd, E is odd, and D is odd. So this is neither. All right. So now we need to take a look at Hamilton. Can I start at any point that I want, touch every point, and not go back to the beginning? Try it. If I leave A, where do you want to go? F,
B,
B,
G,
G,
Z,
E,
C,
C,
D.
D. Yes, we've got a Hamilton path.
easy.
Do you have a Hamilton circuit, though? Is there a way that you can cross all of those and go back to the beginning? So paths and circuits still haven't changed. Path goes from one dot and ends at a different dot. A circuit goes back to the beginning. Is there a way we can do it?
Yes.
Yeah.
Dakota says yes. I hear some other yeses.
Wait, can you say that again?
What, the circuit and path?
What you just
Okay,
said.
so a path, you start at one dot and you end at some other dot somewhere else. A circuit always starts at a dot and you make your way back to that.
Go back.
So kind of like you leave home and you go to Target, you go to Walmart, you go to Food Lion and you go back home. That's a circuit. If you would leave and you would go to all these stores and then you would go to Amaya's house to hang out and stay there for the night, that's a path. Okay. All right, so how did you tell me now? Where we going? A to F,
E to D,
E to D,
CG,
CG,
BA.
B, and back to A. So yes, there is a Hamilton circuit in this one as well. Okay. Take a look at graph number 2. Is there a path?
Yes.
Yes. I can touch every dot and end at a separate dot.
Oh, yeah.
No.
Okay. There is no circuit here though. You can never make it back to E. There's a bridge that leads you out to E. There's not another way to get there. So this is a no. There is no circuit.
It's a path.
Okay. You say yes on a path for this one? Yeah, I can do this. Okay. Is there a circuit?
Yeah.
Yes, there's also a circuit. How do I have to trace this to get a circuit though?
A, D, C, E, B,
A, D, C, E, B, A. Something like that. Okay. So there is a circuit as well. You could have went A, D, E, C, B, A. Okay. There was multiple different circuits here. Take a look at graph number 4.
A. No, no path.
No path?
Yes, it is.
Yeah, there's a thing.
There's a path.
It's no circuit.
Oh, like I'm on
There's
the-
no circuit.
Oh.
There is no
I was
circuit
on
in that
graph
one.
number 5.
Okay. You were looking at graph 5?
Yeah.
You going too fast?
No, I'm talking about him.
No.
We already on graph five. It's no path.
I agree. There is no path here. Watch what happens. If I leave D and go to E, I can go to C, B. I get stuck.
Yeah, 'cause you said-
Okay. If there was an extra line that went from F to G to C, you'd be good.
Wait.
Okay. No, go ahead, Amaya.
No, I'm confused myself.
No, you're fine. Where you want to go? We'll talk through it.
Okay, go back to start going how you just went.
Okay.
I'm gonna tell you when to stop.
So go this way.
Yeah. No. Can you not hit the middle?
There's no line that leads from C to the middle. There is no line here, so you can't go.
So that's why you can't hit F and A?
Okay. So even if you would try to leave here and go to E and go to G, you go to B and you can either go to C and you're stuck, go to F and you're stuck, or go to A and you're stuck. Okay. There's no way to do it. So there is no path.
And there is no circuit.
There is also no circuit. Okay. What about 6?
It's
There's a path,
There's a path,
but not a circuit.
but not a circuit. Okay.
A, B.
So you can go A to B to F, take this whole diagonal straight down over to E and down to D.
That's right.
That is a path. but there is no way to get back to A. There is no circuit. So the question below that says, do you notice a relationship between the graph having a Euler and a Hamilton circuit or path? Is there any type of pattern going on here?
No.
No. Okay. Unfortunately, there is no way for me to tell you like it was with Euler, where I can say if you have all even vertices, you have a circuit. There is no trend for Hamilton. Okay.
Well, then
That's
we
the
figured it out.
hardest part about this chapter. Okay. And we're going to learn some formulas today, and you all hate formulas.
Oh,
I will tell you this, you will get a note card for your test,
thank you.
and we'll give you a note card.
All
All right. So, some helpful hints on how to find these Hamilton circuits. Okay. A vertice of degree 1 or 2 are very helpful because they represent required edges that must be used to reach that vertex. So, what that means is when A has a degree of 1, we've got to use that edge. Okay, because we have to reach A. Okay, so that's all that's telling you. So let's look at this graph up on the right. A, B, C, D. Okay, so it gives me your first Hamilton circuit. A, B, C, D, A. I'm going to write that down here so it's all together. Okay. We have circuits that are shifts of that. Okay. What that means is instead of starting at A, we're going to start at B. So a shift Hamilton circuit would look like B to C to D to A and back to B. So you didn't change the order of it, you just changed your starting point. This is the same Hamilton circuit as A, B, C, D, A. You still went in the same order. Okay. You can also do it with C and D. So we can start with C. C goes to D, to A, to B, and back to C. Because we have 4 dots, there's one more. So we can go D, to A, to B, to C, and back to D. Okay. So those all represent the same circuit. Then we've got something called distinct Hamilton circuits. These go a different way. So the easiest way to do this is to do them all starting at the same letter. So we've got 1, A, B, C, D, and A. That was the first one we started with. Okay.
Do you mean like going like A, B, C, B, A?
Okay, so Destiny just found our first one. So the first distinct one is to do this one in reverse order. So go A, D, C, B, A. You went in a completely different order than the first one did. Okay, you went backwards. What is another way that I can write this that we start at A?
A, C, D, B.
A, C, D, B, A. Okay, that doesn't match anything you have up there. And just like the first one, you can do it in reverse order. So we can do A, B, D, C, and back to A.
So you can cross it.
You're not crossing a vertex twice, though. You're just going back to the starting point. So if I leave A, I can go to B, to C, to D, and back to A. So I only visited each dot once. Okay. Remember, with Hamilton, you don't have to touch every edge. So just crossing those outside edges are fine. Okay. It's completely different, though, if I start at A and go in the reverse order, which is what you gave me. I can leave A and go to D, go to C, go to B, and back to A. Okay. And then Baden gave me a completely different approach. I can start at A, and I can use my diagonal and go to C, go to D, go to B, and back to A. You're still going to every place once, but you're going in a different order. So finding all of your distinct Hamilton circuits is trying to find all the different orders that you can do. Okay. There should be one more. ADBCA. Perfect. ADBCA. Which means I can also do the reverse order and go ACBDA. Questions? What did I do with that page? The page is missing. All right, that's all. Okay, example number 1. It says list all of the possible Hamilton circuits starting at vertex A. Now take a look, because I gave you a hint. There are 8 total distinct circuits. Okay, remember though, just like we did here, this and this are 2 different circuits. So right here, this graph had 6 distinct circuits. So technically we only need to find 4 and then use their reverses. So let's see if we can do it. You said A, B, C, D, E, F, G, and back to A. So we can go in alphabetical order. A, B, C, D, E, F, G, and back to A. Which means we have a second one that goes backwards. A, G, F, E, D, C, B, and A. So there's 2. You said A, G, what? Careful, you don't want to go.
Right. Can you do
Okay, hold on. Let me erase this. And you said we can go A, G, go B, E, I. You have to hit D. So I would go D, C, F, and back to A. Good. A, G, B, E, D, C, F, and back to A. Again, that means we've got a reverse of A, F, C, D, E, B, G, A. Some of these are hard. Okay, this is going to be a little bit tougher than the last chapter.
We have to start with A.
I would always start with A because that's what helps make them distinct. Because if you start with another letter, you could have the same thing, it's just shifted, like we did in the first one. Okay, so stick with your same letter when you're doing distinct. What you got, Dakota?
A,
Okay,
G,
A to G,
B,
B
to C,
to C
to D,
to D
to E,
to E.
to F, to A,
Fantastic. That one works too.
and then back.
A, G, B, C, D, E, F, and back to A. Which again means I can do A, F, E, D, C, B, G, and back to A.
So we need one.
And then I got another one.
You got one? Destiny thinks she's got her last one. Let's go.
Okay. A, B,
A to B,
E,
E. Okay.
E,
You said where?
E,
D. Okay.
C, F, A,
G, A.
E,
Okay. A, B, E. That's A, B, C. That's. I'm just checking and making sure we don't have anything. Nope, that's good. Fantastic, Destiny. A, B, E to D to C to F to G to A.
And back.
And then you can do it backwards. A, G, F, C, D, E, B, and A. You found them all. Okay. So again, what makes them distinct is none of these go in the same direction. Okay. It's all like, instead of going to Food Lion first, I'm going to Walmart first. Or instead of going to Walmart first, I'm going to, I don't know, Old Navy first. Okay. You're going to different places at different times. What do you think? How many Hamilton circuits do you think that you would have that would start at B? If I had 8 that started with A, how many would you have that started at B? 8. What about F? 8. You would have 8 distinct circuits that started any given letter. So 8 distinct circuits that can start at any letter. So if I give you a different starting point, you still have the same amount of circuits going on. Question. We're almost done with 6.1. Okay. Example number 2. Find a Hamiltonian path that begins at A and ends at E. Okay, remember, your rule is you must touch every dot. It does not matter about your lines. So,
A, F, B, C, G, D.
woo! I heard A, F, B, C, G, D, E. Okay? You could have gone A, D, G, C, B. Oh, no, that wouldn't work, would it? No, that wouldn't work. Is that the only one?
Yeah.
I think so, too. A to F to B to C to G to D and to E.
Because even if you go like A, B, C, G, D, you can't
You
get
can't
back
get to
up.
F without crossing A again.
Yeah.
Okay? Find a Hamiltonian circuit that's going to start at A and end E to A.
It's the same one, just added
It's the same stinking thing. You just add A onto the end. You're already at E. You just need to jump to A. So A, F, B, C, G, D, E, A. EA Sports. Get your head in the game. Or something like that. Get in the game.
It's in the game.
It's in the game. Okay. I don't know. I don't pay attention. Okay.
Oh, I got one.
Find a Hamilton path that begins with F and will end at G.
F, A,
A,
B.
B, no, F, B, A.
F, B, A. You said E,
C,
C, D, G.
yeah.
Okay? That one works. So F, B, A, E, C, D, and back to, and ends at G.
Another one, F, A, B, E, D, C, G.
And you said which one worked?
F, A, B,
F, A, B,
E, D, C.
E, D, C, and G. Okay, so you could have had that one too. You could have left and went to A before you went to B. Okay. So again, this is another chapter where you're going to have multiple ways to do things. Example number 3. The following graph has no Hamiltonian circuits or paths. Why?
The vertices out, out in.
All of these vertices out on the edges. What's wrong with them?
Can't get to it. Like,
You can get to them, but you can't
There's so many.
You can't leave them.
Yeah.
Okay? They're kind of little islands where they only have one way to get there. So once you've gone across that and you're at that dot, you can't get back. Okay? So you're stuck.
So you can't leave the bridge
Stuck at dot.
vertices.
I just put bridges.
Okay? You can put bridges because that's exactly what those are. You've got 4 bridges that won't allow you to come back to the mainland. Okay?
that would be awesome.
Find all circuits that start with A.
Find all of the Hamilton circuits that start at A.
How many is it?
The circuit the one that just goes to each vertex.
Yes, the circuit, because we're talking Hamilton, you only have to go to the dot and back. There's the page I was looking for. Okay. There are 6 distinct ones.
Okay.
Okay, we've got 6.
A, B,
A, D, F, C, B.
Okay, you said A, D, F,
C, B.
C, B.
Oh, it gotta go back.
I can't go back to A. That's not going to work.
Oh, A, B, F, E, C, A.
You said A, B,
I said A. Yeah, you can do A, B, A, B, E, B.
A, B, E, D, F, C, and back to A. Okay.
And vice versa.
So we did A, B, E, D, F, C, and back to A. Or again, I can do the reverse. A, C, F, D, E, B, and back to A. So you've got 2.
I got one.
You got one? Who's got one? All right. What you got, Hyro?
A, D.
A, B.
And back to A.
Fantastic. There's another one. Hyro went from A to D to E to F to C to B and back to A. And as always, we can go in reverse. A, B, C, F, E, D, and back to A. There should be one more.
A, C,
D, E, B, C, A.
A, C, F, D, E, B, A.
A, D,
No.
E, B. That's not going to work.
I just told you,
ADF.
Ms. Smith.
Hold on.
F, D, A.
A, B, F.
All right, Dakota, tell me.
Oh, wait, it's gonna be the same one.
A, C,
A, C,
F, D,
F, D,
E, B, A.
E, B, A. A, C, F, D, E, B, A.
It's
It's that one.
I just said one.
You already have it.
That wasn't up to the
What you got, Kayla?
A, B,
Hold on. A, D,
F, E.
F, E.
Oh, wait, it's already up there.
Wait, hold on.
Yeah,
No,
B, C, A.
BCA.
Does that one work? B, C, A. A, D. Yeah, because all you did was change what Hyro did. Hyro went E, F. You went F, E. That works. Good. A, D. It's the slightest change that changes your circuit. So A, D, F, E instead of E, F. C, no, B, C, A. Sorry, B, C, A.
A, B, F.
B, C, A. And then in reverse, A, C, B, E, F, D, and A. Okay. Find all Hamilton circuits that start at D. We want to start at D. Okay.
D, A.
Okay. There's 6 of them. Watch. Watch what I do. You ready? So
Oh.
just look here and shift them. So all we're going to do is start at D. So this first one is D, F, C, A, B, E, D. I went in the same order that this was in. I just shifted and started here instead of at A. And then, of course, you can do this in reverse order. D, E, B, A, C, F, D.
D, F.
Okay. You can do the same thing with the next step down. So we're going to start here. D, E, F, C, B, A, and back to D. So then you've got D, A, B, C, F, E, D. And you'll do the same thing with your last one. We're going to start at D. So D, F, E, B, C, A, D. And of course the reverse, D, A, C, B, E, F, and D. Questions? Okay, that was 6.1.
Can you go back to
Okay.
the
Yes. You're welcome.
They can't be still coming in here.
You messed up.
Yeah, it's not right.
If they come in here now, I swear to God.
Who is that?
You good?
Section 6.2 today?
Okay.
Right, I'm cold. It's
Okay. The last concept we need to talk about is a complete graph. This should not take us long. Okay, a complete graph is in which every pair of distinct vertices is joined by exactly one edge. So what that means is these two dots only have one line that connect them. These two dots only have one line that connect them. So on and so forth. So what you can't have in a complete graph are multiple edges. Doesn't work. So, notation, K sub n. K means that you have a complete graph, and n is the number of vertices you have. So, this is K sub 3. It's a complete graph, and it has 3 vertices. This one would be K sub 4 and K sub 5. We're going to discover all the formulas for this. Okay, so let's see if you can answer these questions that go along with it. Do you think a complete graph has to be connected? Yes. It tells you right up at the top that every pair of distinct vertices is joined by exactly one edge, which means they're all together. It must be a complete graph. Number 2 says, is a complete graph allowed to have loops? No. The dot has to be connected to another dot. They're distinct vertices, so they're 2 separate dots. They cannot be connected to each other. So there are no loops in a complete graph. Can I have multiple edges? No. Again, your definition says every pair of distinct vertices is joined by exactly one edge. You cannot have more than one. And finally, can different vertices have a different degree?
Yes. Look.
Hold on. Take a look at this. In this first graph, what's this degree?
2.
2, 2, 2. What about this one? 3, 3, 3, 3. What about this one? 4, 4, 4, 4, 4. So this is a no. In your complete graph, all of your vertices will have the same degree. What is the relationship between the degree of the vertex and the number of vertices in the graph? So this has 3 vertices, degree of 2. 4 vertices, degree of 3. 5 vertices, degree of 4. Your degree is always 1 less than the number of vertices that you have. Okay. So, degree equals number of vertices minus 1. Or we can also write it, the number of vertices equals the degree plus 1. Okay. You can write it 2 different ways. So that way, whether they tell you your degree is 7, you should be able to tell me, well, I have 8 vertices then. Or if I tell you you have 10 vertices, you should be able to tell me each has a degree of 9.
Wouldn't it be Kn minus 1? Like an actual.
Huh?
Wouldn't it be like Kn minus 1?
Oh, Jesus.
What if they walk in when it's time to go? I'm walking out. I'm not standing here.
Right.
Oh, no, y'all go on. Let's see if we can get through this.
Miss Smith will entertain.
Huh?
Watch a lot of
You know, entertain the people that come in.
Yeah, they're gonna watch me eat my yogurt. Okay, so you should be able to fill in this row. Okay, so if I'm at K sub 3, I have degree of 2, and how many vertices do I have? 3. Okay, you've got a degree of 2 and your vertices are a 3. Okay, if I have k sub 4, my degree is 3 and my vertices 4. Okay, so k sub 5 is a degree of 4, vertices are 5, and 6, degree of 5, vertices are 6. Okay, now I'm going to go back and give you this column and see if we can come up with the formulas. So I'm going to tell you that the total degree is 6. Your total degree here is 12. This is 20. And this is 30. Can you tell me where I got those numbers from?
2 times 3.
2 times 4.
So it's gonna be D.
This is 2 times 3 gives me 6. My degree times my vertice will always give me my total degree of my graph. So over here where it says, how can you calculate the total degree? You take your number of vertices and you multiply that by the degree. That's fine. D times V if you know what those mean. How many edges are in K sub n? Okay, you remember back when we did pairwise comparisons? And I told you take that number times 1 less and then divide it by 2. Guess, listen, that formula is coming back to haunt you anyway, even if you don't remember it. Okay, so to get this, it's n times n minus 1 divided by 2. Okay, in this chapter, n represents your vertices times your degree divided by 2. So what that means is if this graph up here has 6 total degrees divided by 2, that means you have 3 edges. Okay, so your total amount of degrees divided by 2 will give you your number of edges. So you can also add this in here. Total degree divided by 2. All of these, all 3 of these equations are the same exact thing. They're just 3 different ways to look at it. Okay. So this graph with a 12 total degree, it has 6 edges in it. A graph with a 20 total degree has 10 edges in it. Okay, so all of the formulas that I just gave you, if I have a complete graph that's K sub n, we have n vertices. The number that replaces n is how many vertices you have. Your degree then is n minus 1. It's 1 less than your vertices. And your number of edges is n times n minus 1 divided by 2. So you would take this and this, multiply them together, and then divide that answer by 2. And that's all we got. Okay.